In 2020, Elon Musk confidentially declared that his company would land the first human on Mars by 2026. It's now 2024, and from what we can see, Musk hasn't had any luck. And with just 2 years remaining until his predicted date, the prospect of seeing a human on Mars is, to put it mildly, unlikely. The goal was audacious.
That's rate of base. We are seeing G's on the order of 11.
To find out if life could ever have existed on Mars.
Thrusters have been reading. We're at 9
Signals Odyssey is still strong.
On February 18, 2021, a Perseverance rover successfully touched down on Mars. It cost a total of $2.5 billion. It has many scientific instruments to help study Mars, search for signs of life, and prepare the way for future human explorers. Perseverance is, of course, not the first rover to visit Mars. Sojourner was in 1997, a very small rover. And here's a person for size comparison. Spirit and Opportunity in 2004. These were identical rovers, sent just a few weeks apart from each other. Curiosity landed in 2012. And then Perseverance in 2021. Same size as Curiosity, but much more advanced technology. This is not a complete list. This just shows the most recent rovers sent by NASA in the United States. For most of this video, I'll be focusing on Perseverance. NASA designs and builds the rovers in Pasadena, California at the Jet Propulsion Laboratory, or JPL for short. This took about 8 years of designing, building, and testing to get Perseverance ready to go. It was built in a clean room that's free from dust or other contaminants. It's designed to work on another planet, different atmosphere, different gravity, and most of all, no repair station. It has to be engineered so well that it can last for years on its own. On top of that, it has to be light and compact so it can fit inside of the launch vehicle. Once it was ready to go, the rover was carefully packaged up and then flown across the United States to Kennedy Space Center in Florida. This is where the launch happened, the same place that NASA has been launching rockets since the 1960s. Perseverance was installed along with several other components that went along for the journey to Mars. We'll talk about each one of these pieces later in the video. This was all put inside of the payload fairing, then taken to the rocket, and then lifted up to the very top. This rocket is called an Atlas V. It's made by a company called the United Launch Alliance, or ULA for short. Let me point out that the rover was actually upside down for the launch. The best time to launch to Mars is about every 26 months. If we show this with the correct scale, you can barely even see the sun. With this animation, I'm going to show this out of scale so we can see this a little better. For the Earth to get around the sun, it takes exactly 1 year, right? No surprises there. Mars, on the other hand, takes almost 2 years to get around the sun. The best time to launch is right before Earth and Mars are lined up. This is called a launch window, and it happens about every 26 months. Perseverance was launched on July 30th, 2020. The 4 solid rocket boosters use up all their fuel first. At 1 minute 49 seconds, they are jettisoned or separated from the rocket. At 3 minutes 27 seconds, the payload fairing is jettisoned, which exposes the spacecraft. Next up, the main booster runs out of fuel. At 4 minutes 28 seconds, the main booster is separated, and it will fall back to the Earth. This is called the Centaur stage. Its main engine now fires up. This is what gets us into orbit around the Earth. At 11 minutes and 30 seconds, the engines shut off. This is called the coast phase. We'll stay here for about a half hour. It's a good time to check things out and make sure that everything is still working as it should. And then we relight the engines for about 8 minutes. This is called the Earth escape burn. This is what gets us on a path towards Mars. Then the spacecraft separates. It's traveling at 41,000 kilometers per hour. And it will take about 7 months to reach Mars. Our spacecraft is made up of a few pieces. Here's the rover, all folded up inside, the descent stage, this has 8 rocket engines on it, the heat shield, which slows us down to the atmosphere and protects the rover, a back shell, which protects the rover as it descends to the surface of Mars, and this is the cruise stage, provides power, fuel tanks, and thrusters, and also keeps in communication with Earth. This whole assembly stays together during the 7-month journey to Mars. We'll need to adjust our path along the way. We do this with the thrusters on the side of the cruise stage. This is called a trajectory correction maneuver, or TCM, and there are several of them on the way to Mars. Landing on the surface of Mars is nothing short of intense. They call this EDL, or Entry, Descent, and Landing, often nicknamed the 7 minutes of terror. This is because if anything goes wrong, then we'll likely fail to get the rover safely to the surface. At the time of landing, it will take about 11 minutes for any signals to reach Earth. This is, of course, traveling at the speed of light, the fastest that we know how to communicate. It doesn't seem very fast, does it? 11 minutes is a long time. To put this in perspective, from Earth to the Moon, light takes just over 1 second to get there. When the Apollo astronauts were landing on the Moon, NASA could communicate with them almost in real time. It would take about 2.5 seconds to receive a reply. On Mars, this is completely different. If something goes wrong during the landing, Mission Control won't hear about it for 11 minutes. And any reply would take another 11 minutes to get all the way back. By this point, it will already be over, either a safe landing or a crash. This means the computers, electronics, and the software must be smart enough to do everything on their own. EDL, Entry, Descent, and Landing. Let's follow this through step by step. About 10 minutes before entering the atmosphere, the cruise stage is detached because it's no longer needed. Small thrusters on the back shell will now be used to steer the spacecraft. Next comes atmospheric entry. The heat shield will protect the rover during this time. Once we get about 11 kilometers above the ground, then the parachute can deploy. It uses a technology called range trigger, which finds out how close we are from the landing site and then deploys the parachute at just the right moment. Next step is heat shield separation. For the first time, the Perseverance rover can now see the Martian surface down below. Now we use terrain relative navigation. The rover will be taking pictures of the ground beneath it and comparing these to maps of Mars. This will be used to safely steer the rover towards the intended landing site. Next comes back shell separation. All that's left is the descent stage and the rover. The rockets on the descent stage fire up to slow us down as we get closer to the surface. Then the rover separates but still attached by some cables. They call this the sky crane maneuver. The final part everyone is waiting for, touchdown. The cables are cut and the descent stage flies off into the distance for a crash landing far away from the rover. And if the planet is safe enough now for human explorers.
Altitude of 8 kilometers. Valid range.
Feature has separated. We have fired the ground with the radar. Standing by for back shell separation.
Just getting to the surface was risky.
We are in hard flight. 500 meters in altitude. We found a nice flat place. Standing by for sky crane.
Requiring technologies never before tried.
Sky crane is started.
Her journey was going to be complicated and dangerous.
Signal to us, you remain strong.
Tango Delta nominal.
All alone on Mars, the robotic rover would have to learn and adapt.
UHF is good. Touchdown confirmed. We're seeing Mars.
And so would her human handlers. Now it's time to check out the rover's systems, deploy the mast, and then the robotic arm in the very front. The main purpose of the Perseverance rover is to look for signs of life. It landed in Jezero crater, which, billions of years ago, used to be filled with water. Where there is water, there is usually life, or at least signs that life existed in the past. Perseverance rover has an array of advanced scientific instruments to study the surface of Mars. If you remember from earlier, the rover is enormous. It's about the size of a car. The main body of the rover they call the Webb, Warm Electronics Box. Then you've got 6 wheels, 3 on each side, that are made of aluminum. The front and back wheels can turn, allowing the rover to spin a full 360 degrees. The suspension system allows the rover to travel over rough terrain. You never know what kind of obstacles you're going to come across on Mars. But to be more realistic, the rover would be going about this fast. It has a top speed of 0.1 kilometers per hour. The slow speed is mainly for the safety and stability of the rover. This is the remote sensing mast. This is the place where you'll find some of the cameras and sensors of the rover. It's just a little taller than the height of a human. The idea is to give us a similar view of what a person would see if they were here on Mars. This big circle up on top is called the supercam. It's basically a laser that can identify chemicals in rocks from as much as 7 meters away. This is the Mast Cam Z. These are the main cameras on the rover that can even take high-definition video. Navigation cameras are used to help the rover safely drive on the surface of Mars. Right below is the Mars Environmental Dynamics Analyzer, or MEDA. This is studying the weather and atmosphere on Mars. The rover has 2 microphones, one on the mast, and then another on the side of the rover. Then we have the HazCams, which is short for Hazard Camera. There's some in the front here, but also in the back. Like the name says, these cameras help avoid hazards and obstacles while driving around on Mars. The power source for the rover is called the Radioisotope Thermoelectric Generator, or RTG for short. It's a nuclear power source. The decay of radioactive elements generates heat, which can then be turned into electricity. Some of the previous rovers used solar panels to generate power from the sunlight, but this doesn't work at night, and if too much dust gets on it, well, then it's game over. Both Curiosity and Perseverance use the RTG, which means a lot more flexibility in regards to power. This is RIMFAX, or Radar Imager for Mars Subsurface Experiment. This uses radar waves to study the ground up to 9 meters below the surface of Mars. Then there's MOXIE, Mars Oxygen In Situ Resource Utilization Experiment. This takes the carbon dioxide on Mars and turns it into oxygen. This kind of technology will be very important once we start sending humans to Mars. And of course, the robot arm in the very front of the rover. This has a few tools at the end with some really big NASA acronyms. So here we go. PIXL. This helps to determine what chemicals make up the rocks on a very small scale. Watson, another powerful camera to see the rocks with fine detail. And then Sherlock. This provides fine-scale imaging. At the end of the arm is the coring drill. This is capable of drilling and collecting samples that will be stored on board the rover. Then it will take these samples and place them inside of the rover. Future mission is planned to take these samples from the surface of Mars and return them to Earth so we can study them further. So how does Perseverance communicate back to Earth? The best way is to use the Mars Relay Network, which consists of several satellites in orbit around Mars. These were launched long before Perseverance got to Mars. These satellites are also used for science and to communicate with other rovers that are also on Mars. For example, one of these satellites is called the Mars Reconnaissance Orbiter. So Perseverance can send data to the satellite, which will then send it directly back home to Earth. On the surface of Earth, NASA uses massive satellite dishes to communicate with spacecraft throughout the solar system. This is part of the Deep Space Network. There are 3 main locations for these satellite dishes: Goldstone, California, Madrid, Spain, and Canberra, Australia. No matter which way the Earth is facing, it will always be able to receive signals from Mars or other distant places in our solar system. Perseverance has 3 antennas on board. The UHF antenna, ultra-high frequency antenna. This communicates directly with satellites above, primarily used to send large amounts of information. The high-gain antenna transmits directly to and from Earth, and then the low-gain antenna, mostly used just to receive data from Earth. Of course, we can't forget about Ingenuity. This is the helicopter that was sent to Mars along with the rover. Now, where would you put a helicopter on the rover? Look closely, you'll see a little tiny black compartment right here. This is where it was stored. About 2 months after landing, the helicopter was finally deployed onto the surface. The process took about a week to complete. First, the cover is removed and we expose the helicopter. Then it's unlatched, carefully folded down, the legs come out, and dropped onto the surface. Perseverance can drive away and Ingenuity can start to absorb the sunlight on its solar panels. The helicopter has 2 rotors that rotate in opposite directions. On Earth, most helicopter blades spin at only a few hundred RPMs, or rotations per minute. For a helicopter to work on Mars, we have to spin the blades a lot faster. This is because the air is much thinner here. The first test flight of Ingenuity happened about 2 months after landing on Mars, the first helicopter to fly around on another planet, and it turned out to be a huge success. As of this video, there's been a handful of flights and Ingenuity is still operational. Perseverance paves the way for future missions where we will hopefully be able to return Martian samples back to Earth. And of course, the next major milestone, sending humans to Mars. We are down. But where are we? There's the peak of Aeolus Mons, better known to the team as Mount Sharp. Our descent imaging camera is, unexpectedly, still working. We'll have an extra eye on the ground throughout the mission. And we are not alone. Mars Odyssey, Mars Express, and the Mars Reconnaissance Orbiter monitored the landing from orbit, relaying our telemetry through the Deep Space Network. Their timing was perfect. The high-rise camera aboard the reconnaissance orbiter captured us descending on parachute. The day here lasts 24 hours, 39 minutes, 35.24 seconds, nearly 40 minutes longer than an Earth day. It's called a sol. Above, high-rise has found us. The back shell, descent stage, our heat shield, even craters left by the tungsten ballast weights. We're about 10 kilometers from the base of Mount Sharp, our ultimate goal. It's the most accurate Mars landing yet achieved. We deploy our high-gain antenna. Now, we can talk directly to Earth. It's time to put up our mast. A series of navcam images are assembled into our first selfie. Engineers had worried that dust kicked up by braking rockets would cover the rover. But Curiosity's decks appear mostly clear and ready for action. The team at JPL wipes more than 500,000 lines of entry, descent, and landing code, replacing it with surface mission instructions. Curiosity's onboard computers are a pair of radiation-hardened PowerPC chips bused to 2 gigabytes of flash memory and 256 megabytes of dynamic RAM. It takes the next 7 sols to upload and check the new software. Then, we are a spacecraft no longer, but a rover, eager to explore. Curiosity is a direct descendant of Tiny Sojourner, the 1997 Mars Pathfinder rover, and a big brother to the rover's Spirit, now asleep on Mars. And Opportunity, still doing science about 7,000 kilometers away. Designed and built at NASA Caltech's Jet Propulsion Laboratory, every component of this rolling lab was tested, tweaked, retested, and refined. They sent power to the drive motors, performed a traditional shake and bake test, severe vibration, then heating and chilling in a vacuum chamber. They tested its ground-finding radar from an FA-18 Hornet jet and an AS-350 helicopter flying over terrain similar to Mars. They invented and perfected its supersonic parachute design. At the speed Curiosity would travel in the high Martian atmosphere, the chute would fill or fail in a fraction of a second. Test data would only have meaning if the team could see the failure modes. So these became the best photographed parachute inflations in history. They tried out their risky sky crane deployment with all of JPL watching.
2, 1, fire.
After long debate, the science team settled on a landing site, Gale Crater. At its center, Mount Sharp is built in layers, clays at the bottom, sulfur and oxygen-bearing minerals above, and complex channels carved long ago by flowing liquid at every altitude. The mountain offers a chance to voyage up through millions of years of geologic time on Mars. We've taken the frames of a complete panoramic picture now. Rocket blasts from our sky crane have scoured the surface in places which appear as light gray smudges. The geologists are fascinated by what the thrusters have uncovered. Curiosity's ChemCam finds its calibration marks mounted aft next to our onboard nuclear power source. By zapping bits of Mars with its infrared laser, Curiosity can tell what a rock is made of from up to 7 meters away. We target a fist-sized rock named Coronation, vaporizing a tiny area with a pulse hotter than the surface of the sun. We record the spectrum of the plasma ball from ultraviolet through infrared. The laser melts a spot less than 1 millimeter across. So we send a series of pulses to cover the mineral's variations. On Sol 20, ChemCam sends down its first raster of 5 side-by-side laser blasts. Our wheels print the letters JPL on Mars in Morse code to check if we're slipping on terrain. Rover drivers are eager to test Curiosity's navigation systems. Using visual odometry, the rover can drive short stretches all on its own. By Sol 26, we've driven over 100 meters, more than a football field length. Road test behind her, she's licensed to drive on Mars. About 300 meters ahead, the cameras see a place where 3 different terrain types flow together. We call it Glenelg. That's a palindrome, the same word read forward and backward, because we'll visit it on the way in and again on the way out. Long before Curiosity touched down, the geology team created a map based on orbiter images. They overlaid a grid. Each box, 1.5 kilometers on a side, is named for an Earth town of less than 100,000 inhabitants. When the team spots a noteworthy object, they name it after a geologic feature from its hometown on Earth. Curiosity's arm-mounted Mars Hand Lens Imager, or MOLLE, is much more than just a selfie stick. Like Sherlock Holmes, the rover carries this MOLLE magnifying glass to look closely at clues to past events. Curiosity can also examine herself. All is in order. MOLLE snaps its calibration target, including a 1909 Lincoln copper penny. The team now rotates the turret 90 degrees to calibrate the alpha particle X-ray spectrometer. If MOLLE is the rover's eye, then APXS is her nose. Between MOLLE and APXS is the sampling drill, with a brush-like dust removal tool, the DRT. Rounding out the tool turret is the complex Chimera. It can scoop soil, then sieve, sift, and send the sample into 2 labs located inside the rover. To do this, Curiosity executes an elaborate hip-hop dance of precision robotics. Watching Chimera pop and lock reminds us of Curiosity's actual size. None of her cameras can capture more than 2 megapixels. But by stitching images together, the rover teams get all the resolution they need. To precisely position Curiosity on a science target, rover drivers visualize various paths on a 3D terrain map, which can be lit for any time in the Martian day. On Sol 44, the APXS is tasked with making its first science sniff, and the MOLLE its first science close-up of a Mars rock. We name the rock Jake Matievich, to honor our friend and mentor who had passed away just after we landed. Every six-wheeled Mars rover owes its basic design to Jake, the JPL mathematician turned engineer who was a driving force of the 1997 Sojourner rover. Through some clever improvising, the team gets APXS and MOLI data of a spot already shot by ChemCam. We quickly determine that Jake's rock was born in an ancient volcano. This is Mars rover science at its best. Jake would have been proud. We have gathered enough data to make a bold announcement.
This is a rock that was formed in the presence of water.
Mars may not now be inhabited, but it definitely could have been. Our mission has found abundant evidence that water flowed here on ancient Mars and did so for a long time. It turns out Curiosity landed close to the end of an ancient river flowing out of Gale Crater's ring of hills. Rivers flowed down the slopes of Mount Sharp as well. As they hit flatter ground, these rivers splintered into many smaller streams, spreading out into an alluvial fan. We can now confirm something else scientists have long suspected. Mars' atmosphere was much thicker in the past, and it held much more water than it does now. Sniffing the air, the SAM experiment notices the thin atmosphere has an unusually high concentration of heavy isotopes of hydrogen, argon, and carbon. This tells the tale. There was once a dense blanket of air around Mars, which was stripped away from the top. The MAVEN orbiter will later confirm that this loss is still happening. Earth's atmosphere is more than 100 times thicker than Mars. Why did the red planet lose its air? It may simply be a matter of gravity. Mars is only about a third the mass of Earth. Still, Mars does have wind and weather. The rover's environmental monitoring station keeps track of air pressure, humidity, temperature, and wind. On many sols at around local noontime, its barometer has recorded small dips in air pressure. These may be similar to the dust devils photographed by both Spirit and Opportunity. But there's no visible evidence of them here in the lowlands of Gale, where winds blow down from Mount Sharp in front of us, or from the crater's rim behind us. These winds are seasonal. Mars' orbit is much more eccentric or elliptical than that of Earth. That means the lengths of seasons vary much more here. Autumn in the southern hemisphere of Mars is the longest season. Spring is the shortest. Curiosity keeps track of seasons using an ancient instrument, a sundial. We take the largest photo yet. 3 different cameras contribute almost 900 images to make this 1.3 billion pixel panorama of Rocknest. Centered on Mount Sharp to the south. We can now visualize the ancient lake lying between where we are and where we're going. After 100 sols of pre-planned systems checks, Curiosity has gone from mechanical robot to field geochemist. As we set off from Rocknest, Curiosity's drivers hand the keys to the science team. From now on, operations will be discovery-driven. The quest for domains of life will rule the mission. The rover is headed for Yellowknife Bay, a shallow depression with remnants of an ancient lake and stream beds. We're keeping our eye on a regional dust storm. It's far to our southwest, and we hope that it weakens before it arrives. We've arrived at Yellowknife Bay. 3 different layers of terrain lie exposed here. It could have been the shoreline of a shallow lake. The lower plate rock is full of spherical bumps, technically called concretions, the calling cards of water that once percolated through mud. Does water flow anywhere on Mars today? The Mars Odyssey and Mars Reconnaissance orbiters have documented seasonal streaks running downhill. Seen mostly at latitudes around Mars' equator, the dark traces appear in late spring or early summer. Researchers call them active slope features. Based on the temperatures at those times, the most likely cause is salty water melting out of subsurface ice. The water, or whatever it is, doesn't flow constantly. And by late summer, the features fade. Curiosity will lose touch with Earth for the entire month of April 2013 as the Sun appears to slip between Earth and Mars, what's known as solar conjunction. So, JPL preloads the rover with 30 sols of autonomous science to do. One group of researchers thinks that a series of matted sheets in Yellowknife Bay look like structures produced on Earth by microbes over 3 billion years ago. Could some of these rocks on Mars have been made by microbes? Mars is now out from behind the Sun. We're eager to do more contact science. We choose another flat, veined rock less than 3 meters away from John Klein. The idea is to perfectly place the rover, her arm, and its turret. Then pick the exact drill location to maximize research and minimize risk. Cumberland is loaded with concretions that likely formed when water evaporated, dumping minerals behind. And so we drill our second 1.6 centimeter shaft into Mars. Then shoot a line of laser zaps to see what's in the tailings. Always learning from our rover, the team uploads new ChemCam code to make sure it never looks directly at the Sun, which could kill the instrument. We've come upon a mini cliff just 50 centimeters tall. It's full of holes, many of which have small islands of other material in them. Is it an igneous volcanic rock that bubbled? A sedimentary mud rock through which gas fizzed? Or liquid percolated? Another mystery. Like watching starships passing in the night, if you sat next to Curiosity looking up through a small telescope, this is what you'd see. Curiosity catches Mars' inner moon Phobos sailing past its smaller outer brother Deimos in real time. Here's how big the Martian moons would look compared to Earth's. They're much smaller, but orbit much closer. On another sol, we stop to observe Mars' tiny moons moving across the face of the Sun. But neither is large enough to totally eclipse the Sun. On the long road to Mount Sharp, we pause at a location called Darwin. In one of the outcroppings, the rock cracked long ago. Fluid carrying minerals filled the crack, then evaporated. While the rock eroded away, the hardened minerals remained. The Mars Hand Lens Imager sends a high-resolution presidential portrait from Mars. At closest focus, each of Molly's pixels captures about 5/10,000ths of an inch. It's not the sharpest camera on Mars, but it's on the most mobile platform, allowing the rover to photograph a wide range of remarkable rocks. The layered terrain of Mount Sharp beckons. We're closer, but we need to get on the road again. We've driven almost 5 kilometers. Curiosity's 6 metal wheels are taking a beating. The hard, jagged surfaces lining the foothills of Mount Sharp have left punctures and dents in her metal tread bands. We adopt the strategy, drive less and drill more, to optimize the scientific harvest. We'll aim for a low sand dune we're calling Dingo Gap, to give us a smoother road to the upper mountain. Overhead, Mars Reconnaissance Orbiter watches us make tracks. ChemChem's telescope snaps an image of Harrison Rock, then zaps it with the laser, revealing again distinctive signs of volcanism. This was a land of fire and water. We're rolling over looking back at our tracks, the dark color resembles mud. Ultraviolet light, unfiltered by the thin atmosphere, we've exposed the truth. It's also critical for understanding the evolution of our solar site. Working mostly in the stable temperature, Sam finds these rocks have undergone much more oxidation. Whale rock. They slipped into an ancient lake. A series of large lakes built up over the 5-kilometer for millions of years. Did a moist Mars long ago nurture life? The team goes. Curiosity brushes the rock named Santa Ana. Machine stays rock solid stable. Now sites like Gale Crater to see rocks up close. Confer with one another. So a new system called On-Site is designed to let how humans and robots will along a pass called Artist's Drive. Plex feature calls out to the science team. Such streams, shallow seas, and hot springs where the water has evaporated and crystallize. Here, Curiosity measures many different minerals intersecting and cutting across each other, including calcium sulfate and magnesium sulfate. Each one sulfate and magnesium sulfate. Each one spiced with traces of elements, iron and fluorine, strongly pointing from far-off lands, hinting at where it came from. On Earth, you see, even on land. Considering all of this, Elon Musk's words about the likely deaths of the first Mars explorers sound frighteningly convincing. It's coming from Musk, who is wannabe known for his optimistic what? Humanity does not intend to give up. We'll stop pessimistic thoughts today and move on to how the optimists plan to get to Mars. Let's take this journey along with them. First, we'll see how NASA, the most iconic space agency in the world, sees this. So, the first problem was actually taking off, getting out of Earth's powerful gravitational pull. Now, this all depends on how much equipment needs to be taken along. Take a look at this space shuttle that performed manned missions to Earth's orbit. It's a huge rocket, 83 feet long. But even it looks like a toy compared to the Saturn V that delivered monstrous rocket one would need to lift all the enormous supplies and equipment required for an Earth. To get this into perspective, let's go back to you need to walk those very same 140 kilometers, about 87 miles, through uninhabited terrain with a full supply of food, water. Here's the kicker. The path will be off-road, but on flat terrain. However, the first kilometer must be covered on a very steep slope. So steep that you might not make it to the top. And even if you do, you might collapse at the top, unable to go any further. Scenario of starting a mission to Mars directly from Earth. It's almost in the lunar surface and a venture station, the power and propulsion element, PPE, and the habitation and logistics outpost, HALO, on the Falcon Heavy rocket, scheduled for 2020. After completing all necessary checks, the Dragon XL supply ship will be launched to the Gateway following the docking of a lunar Starship, which is designed for landing astronauts on the moon. After this, the station will finally receive its first astronauts of the Artemis 4 expedition. What will happen next? Up until the 11th mission, it will be a complex and process. Under the Artemis program, astronauts will build and improve the mission. They will establish a lunar base on the moon, develop lunar infrastructure, and is the last one that NASA has. However, we'll still piece together and while Artemis missions 4 through 11 will primarily focus on the developing infrastructure with the 12th mission, the vision of the main goal, the future might come into focus. Let's imagine how this might unfold. Now, let's envision Artemis 12. First and foremost, astronaut teams will work on and streamline and oxygen from readily available sources, essentially lunar deposits. Of course, this doesn't mean turning rocks into water. It means finding ways to efficiently ice. Studies will be conducted on the moon to search for and extract resources. Including water ice reserves. By the way, on Mars, and not necessarily from water. Recently, the Perseverance Mars rover successfully proved this. It utilized MOXIE, Mars Oxygen In Situ Resource Utilization Experiment, a kit designed to experiment with extracting oxygen from the carbon dioxide in Mars's atmosphere. So the prospects are promising, but let's return there to prepare us for a mission to Mars. During Artemis 13, astronauts will likely refine the rapid construction technology. These technologies will be essential for long-term lunar missions, so they'll have to be for creating habitats on the Moon and Mars. In 2020, it signed a contract with ICON, a company specializing in innovative construction technologies. The idea of using lunar regolith for building bases and protective structures using 3D printing technology is also being considered. Analog missions will be a crucial component of the subsequent program missions, starting with Artemis 14 and continuing, and forecasts indicate with a manned landing on Mars. However, given the shifting timelines of Artemis 2, the actual date for a man gone much further. It's impossible to predict this. There are too many unknowns in this equation. 1. Perseverance is, of course, not the first rover. Perseverance in 2021, same size as Curiosity, but much more advanced technology. This is not a complete list. This just shows the most recent rover sent by NASA in the United States. For most of this video, I'll be focusing on Perseverance, or JPL for short. This took about 8 years of designing, building, and testing to get Perseverance ready to go. It was built in a clean room that's free from dust or other contaminants. It's designed to work on another planet, different atmosphere, different gravity, and most of all, no repair station. It has to be years on its own. On top of that, it has to be light and compact so it can. Once it was ready to go, the rover was carried the same place that NASA has been launching rockets since the 1960s. Up to the very top. This rocket is called an Atlas V. It's made by a company called the United Launch Alliance, or ULA for short. Let me point out that the rover was actually upside down for the launch. Best time to launch to Mars is about every 26 months. If we show this with the correct scale, you can barely even see the sun. For this animation, I'm going to show this out of scale so we can see this a little better there. The 4 solid rocket boosters use up all their fuel first. In seconds, they are jettisoned or separated from the rocket. At 3 minutes 27 seconds, the payload fairing is jettisoned, which exposes the space. This is called the Centaur stage. Its main engine now fires up on the Earth. In 30 seconds, the engine to check things out and make sure that everything is still working as it should. And then we relight the engines for about 8 minutes. This is what gets us on a path towards Mars. Then the spacecraft separates. Our spacecraft is made up of a few pieces. Here's the rover, all folded up inside, the descent stage. This has 8 rocket engines on it. The water. It means finding ways to efficiently process deposits of lunar ice. For this, geological studies will be conducted on the Moon to search for and extract resources, including water ice reserves. By the oxygen can also be extracted on Mars and not necessarily from water. Recently, the Perseverance Mars rover successfully proved this. It utilized resource utilization experiment. A kit designed to experiment with extracting oxygen from the carbon dioxide in Mars's atmosphere. But let's return to the Moon. What else can be done there to prepare us for a mission to Mars? During Artemis 13, astronauts will likely refine the rapid construction technology. These technologies will be essential for long-term lunar missions. So, they'll have to be developed on the Moon first and then transferred to Mars. For this, NASA is exploring innovative approaches. In 2020, it signed a contract with Icon, a company specializing in innovative construction technologies. The idea of using lunar regolith for building bases and protective technology is also being considered. Analog missions will be a crucial component of the subsequent program missions. Starting with Artemis 14 through Artemis 20, NASA will conduct analog tests on the Moon to evaluate the capsules, suites, and life support systems. Efficient surface power system to generate energy on the Moon. This is a pinnacle of engineering. A power plant capable of converting the energy from uranium atom from the lunar station module that provides astronauts with sleeping quarters, work and rest area. Then 2 people will descend to Mars while 2 remain on the orbital station. The astronauts will use a specialized land for use when the crew arrives in orbit. Essentially, this will